Good day, everyone. Welcome to my presentation on object recognition using convolutional neural networks on the Cypher-10 dataset. My name is Arnab Haldar, and today I'll take you through the entire project, from dataset exploration to CNN design to performance evaluation and model improvement. Here's the roadmap for our discussion. We will start by introducing the datasets, including the Cypher-10, MNIST, and additional dataset named Places. Then we'll review the basics of CNNs and walk through the baseline CNN modeling using Cypher-10. We'll analyze its performance, compare it with MNIST results, and then dive into improvements that enhance the model performance. Finally, I will present our project report with key takeaways and conclusions. We start by exploring the datasets utilized for this project. In this project, we primarily use the Cypher-10 dataset, a well-known collection of 60,000 32 x 32 color images in 10 classes. It represents a considerable challenge due to its diversity and complexity. The dataset is publicly available for research. To work with Cypher-10, you need to download it directly from the official website or access it via TensorFlow datasets. However, in our implementation, we have used the source files available in Canvas. There is a source script available in Canvas that ensures that the images are correctly scaled and normalized, which is a crucial step before feeding them into the network. So, reiterating, we're using the files which are available in Canvas and utilizing the starter source code provided to kickstart our project. In contrast, MNIST, which contains handwritten digits, offers near-perfect performance in many cases, as we all will see later. This dataset is also publicly available with a collection of 60,000 images belonging to 10 output classes. We use this dataset to train a convolutional neural network and compared results with that of the Cypher-10. Now, the implementation of a convolutional neural network on the MNIST database is not covered fully in this presentation. However, we have got the metrics, and we would be taking that metric as a benchmark and comparing the results that we have got from the Cypher-10 database and compare it with the MNIST database. Additionally, we have explored the Places dataset. It is a large-scale dataset of scene images. Places provides an excellent opportunity to see how convolutional neural networks perform on more complex image types. It serves as an example of datasets beyond MNIST and the Cypher-10. However, we will be restricting our implementation on MNIST and Cypher-10 for this project only. The exploration of the Places dataset was done as an extra exploration step as a part of this project. And if we look at the features of this particular dataset, it's also publicly available. It's a collection of 2.5 million images which is comparatively lot larger than MNIST and CIFAR10 datasets. Even the image size is 256 cross 256 by default, compared to MNIST and CIFAR10, which is 32 cross 32 by default. The images comprised in this dataset are RGB images of real-life scenery, and the output classes are also staggeringly high. Compared to 10 output classes in MNIST and CIFAR10, in Places dataset, we have 205 output classes. And like all the other datasets, the output classes are mutually exclusive output classes. Before diving into the implementation details, let's review what convolutional neural networks are. Convolutional neural networks are specially designed to process grid-like data, such as images. They use layers that perform convolution operations to extract features like edges, textures, and patterns from input images. The below diagram represents the architecture of a convolutional neural network. Such a network comprises of two subnetworks. The first network is called the feature extraction network, used to extract spatial features from images. And the second layer is a fully connected layer, which is responsible for the final classification operation. Now, if we go deep into the feature learning subnetwork, we can see that it's made of two specific components or layers. The first one is a convolution layer. This convolution layer is responsible for capturing spatial details from images. This convolution layer has an activation function, and we use ReLU as the default activation function for the convolution layer. After the convolution layer, we have a pooling layer, which reduces the dimensions of the image. Now we can have multiple sets of convolution and pooling layers successively in the feature learning stage. Now once we have the output from the feature learning stage, we feed the output as an input to the classification subnetwork. Now the classification subnetwork is nothing but a fully connected layer, as I mentioned before, or it's a multi-layer perceptron. It takes in all the inputs in a flattened manner, and the output is probabilities of the output classes to which this input would belong to. The probability of output classes of which it is the highest would be classified as the output class for the given input. Let's talk about the advantages of using convolutional neural networks. The major advantages of CNNs include their ability to learn spatial hierarchies of features automatically. On top of that, we can achieve a decent level of accuracy in image recognition tasks. Images have a spatial structure. CNNs have spatial awareness built within its architecture. CNNs are able to tackle huge input dimensionalities by local connectivity and parameter sharing. Lastly, the network scales really well if we increase the input size. However, CNNs also do come with challenges, such as the need for large labeled datasets. Training large image datasets lead to very high computational costs. Limited interpretability of the learned features due to the black box nature of the neural network is also another challenge we need to face while using convolutional neural networks. And lastly, as we said in the previous slide, CNNs are really good with image data. Now, what to do if we have non-spatial data as input, for example, sequence data? Convolutional neural networks do not work well with any other data which is not spatial data. So it's not ideal to use a convolutional neural network on sequence data. Now let's take a look at our implementation plan. We start by implementing a baseline model on the CIFAR-10 dataset. Next, we compare the results with the results from a baseline CNN applied on the MNIST dataset. After that, we introduce an improved model and implement it on the CIFAR-10 dataset. Finally, we compare the results between the baseline model and the improved model on the CIFAR-10 dataset. An important note on our implementation: instead of using high-level APIs like Keras, we have implemented our model directly in TensorFlow. This approach gives us more control over the computational graph and training process. By using TensorFlow's core functionalities, we were able to customize our training loops, define precise layer operations, and better understanding the inner workings of our CNN model. This granular control is particularly useful for experimental adjustments and debugging. So, if we come down to the points, we are using TensorFlow 1.x for implementation of the convolutional neural network, and Keras is not being used in this implementation in any capacity. Now, let's dive into the baseline implementation. Here is an overview of the implementation specifications. We are using images from the CIFAR-10 dataset. Each image dimension is 32 cross 32 cross 3. Since it is RGB, the depth of each image is 3. In the dimension, the first two 32s refer to the height and width of an image, and the last 3 refers to the depth. Since it is RGB, the depth is 3. The entire dataset is divided into training set of 50,000 images and a test set of 10,000 images. In the baseline model, we have used one convolution and one pooling layer in the feature extraction subnetwork before feeding it to the fully connected layer. The dimensions before feeding to the fully connected layer is recorded as 16 cross 16 cross 32. Now, what is this 32? The 32 are the 32 image maps that are generated as a part of the feature extraction subnetwork, and the length and width of each image map is 16 cross 16. The training of this baseline model is done in 5,000 steps, and the network is tested every 100 steps using the testing dataset. Moving on to our CNN architecture, our baseline model consists of the following layers. Input layer. This is the layer in which the image was fed as input. Convolution plus ReLU. We apply convolution operations followed by the ReLU activation function to introduce nonlinearity. Pooling layer. A pooling operation, specifically max pooling, is used to reduce spatial dimensions. Fully connected layers. The flattened output is passed through a fully connected layer with ReLU activation. Dropout layer. To help reduce overfitting, a dropout layer is incorporated. Output layer. Finally, a fully connected layer with softmax activation outputs the probabilities across classes. This architecture is designed to balance computational efficiency with the ability to capture image features. Once trained, we evaluated the network on the CIFAR 10 test set, resulting in a baseline accuracy of approximately 64.46%. In our performance analysis, we compared the baseline CNN results on CIFAR 10 with those on MNIST. While the model achieved a high accuracy of around 98.87% on MNIST, a dataset that is inherently less complex, the performance on CIFAR 10 was considerably lower at 64.46%. This discrepancy highlights the additional challenges that CIFAR 10 presents, such as more complex visual features and background noise. It clearly indicates that a deeper and more nuanced neural network might be necessary to capture the variability present in the CIFAR 10 images. Now that we have reviewed our baseline model, let's move on to an improved implementation. In this section, we will walk through the redesigned architecture and the training strategy to achieve better performance on CIFAR 10 dataset. In this improved approach, we continue to use the CIFAR 10 dataset as our testing ground. The focus is on enhancing our convolutional neural network to better capture the complex features inherent in these images, ultimately aiming for a higher classification accuracy. Like the baseline implementation, each image dimension is 32 cross 32 cross 3, representing image height, width, and depth. Since it is RGB, the depth of each image is 3. The entire dataset is divided into a training set of 50,000 images and a test set of 10,000 images, like before. In the improved model, we have used 2 convolution and 2 pooling layers successively before feeding the output to the fully connected layer. The dimensions before feeding to the fully connected layer is recorded as 8 cross 8 cross 64, representing the number and the length and the width of the feature maps generated by the feature extraction subnetwork. If we go into more detail, this neural network generates 64 image maps. Each image map has length of 8 and a width of 8. So we can see that the image maps are more compared to the baseline model, but the size of each image map is smaller than the baseline model. The training is done in 10,000 steps, which is double the amount that we had for the baseline model, and the network is tested every 100 steps using the testing dataset. This slide outlines the enhanced architecture. While we still leverage TensorFlow directly, we have made crucial adjustments to our neural design and training parameters. These include modifying the convolutional layers, altering the pooling strategy, and tweaking regularization methods to help the model generalize better. Compared to the baseline, our new design introduces an additional convolution and pooling stage. The deeper network structure is specifically crafted to extract more detailed spatial hierarchies from the CIFAR-10 images, addressing the limitations we saw earlier. We start with the input image. The first layer applies convolution, followed by a ReLU activation. This is followed by the first pooling layer to reduce spatial dimensions. Next, we add another convolution layer with ReLU activation. Then comes a second pooling layer to further condense the feature maps. The output is then flattened. A fully connected layer with the ReLU activation follows, which is subsequently regularized using a dropout layer. Finally, a fully connected layer with softmax activation produces the output probabilities. This refined layout is not only improved for feature extraction, but also helps the network to learn more robust representations. The improvements raised the model accuracy on the CIFAR-10 dataset from 64.46% to approximately 70.03%, which is a 6% bump in the accuracy. In this slide, we can see the model metrics after implementing the base model of CNN and the improved model of CNN side by side. We have also added the model specifications for both the models. We can see that the improved model has captured 64 feature maps compared to the 32 feature maps for the baseline model. The feature maps are double in the improved model, as we have an additional set of convolution and pooling layers for the improved model. The design features, along with the increased step size, attributed to the 6% increase in the accuracy of the improved model. Let's break down the key factors contributing to the improved performance. Deeper architecture. So by adding another convolutional layer, the model is now capable of learning a richer set of features, which was missing in the baseline model. Enhanced feature extraction. More layers mean more opportunities to capture subtle spatial details. Optimized training. Increasing the step size provided the network with more opportunity to converge on optimal solution. These modifications illustrate that even small architecture changes can significantly affect performance, especially on more challenging datasets like CIFAR 10. Now it's worth noting that this much complexity is not required when we are working with a simpler dataset like MNIST, for which even the baseline model performs in a very good way. Before concluding, let's summarize the key takeaways from this project. Dataset specificity. The complexity of the dataset dictates the necessary model complexity. CIFAR 10 requires a deeper network compared to MNIST. Now there are trade-offs. There is always a trade-off between model complexity and the risk of overfitting. Parameter tuning, such as adjusting the step size, is critical. We don't want to overdo and increase step size to a very large number and overfit the model. No one size fits all. There is no single best practice in machine learning or deep learning. Each dataset may require a tailored approach. These key points form the foundational of our improved implementation strategy, setting the stage for future enhancements and experimentation. In conclusion, our exploration of convolutional neural networks on CIFAR 10 has highlighted both the challenges and opportunities when working with complex image data. By leveraging TensorFlow's core capabilities, we were able to build, train, and refine our model to achieve significant improvements. 6% to be exact. The comparison with MNIST served as a benchmark, reinforcing the importance of tailoring the network architecture to the specific demands of the dataset. Now, looking at all the key points, we have successfully developed the CNN model for image classification on CIFAR 10. The model lacked complexity for the good accuracy which we required as a part of this project, so we improved the model and got the accuracy that we wanted. But finally, there is still room for improvement by tweaking the step size and also by adding more complexity to the network itself. So instead of having 2 subsequent layers of convolution and pooling, we can now have 3 and test it out again. It's good to say that there are other models out there like ImageNet and ResNet which perform better than convolutional neural networks. So the final point is there's always room for improvement by increasing the model complexity or by using another model itself. I hope this presentation has provided valuable insights into convolutional neural network implementations and model optimization techniques. Once again, my name is Arnav Haldar. Thank you for watching this video.